All right, AP Chem, we're looking at how we start to actually calculate the pH for our different acid and basic solutions while we are undergoing a titration. And so there's two types of calculations we can start to see, whether we're working with strong species, both a strong acid and strong base, or if we're working with kind of these buffer regions where we've got a weak species being titrated by a stronger species. And so I'm going to work a bunch of mathematical problems here. Hopefully we're going to keep it pretty impromptu. I'm going to kind of math them as we go just to make sure that we're kind of getting the same answers and that we're making sense of what we actually have going on in the beaker. The one piece that's a little tricky here is the volumes are going to be changing. What doesn't change, however, are the number of moles. And so there's going to be a little bit of calculation here when we start to think about what's going on and how we start to solve these. So I'm going to go ahead and hide so that we can start to write on these and work them out. So our first example problem here, we got 50 mils of a 0.5 molar hydrochloric acid solution being titrated by a 0.5 molar sodium hydroxide solution. What is the pH of the solution after you have added exactly 28 milliliters of sodium hydroxide? Cool. Well, let's think first of all about the reaction. We got hydrochloric acid being added to our sodium hydroxide. Both of these are strong, so it's going to go completely to our water and our salt, in this case, the salt, NaCl. Cool. Because the volumes are changing here, because we're starting with 50 mils, we're adding another 28 mils. We got to change stuff to moles. We need to figure out who's got more moles worth of particles. The good news is we're just working with molarity. Molarity equals moles over liters. So given our two values up above, we can solve for both the acid and for the base. We're going to solve for moles. Well, moles is going to be equal to our molarity times the liters. So for our acid, it's going to be 0.5 molar times our volume in liters, which is going to be 0.050 liters. So 0.5 times 0.05 going to be 0.025. Sorry, 2 sig figs. Yeah. And that's now moles of our acid, HCl. We would do the same for our base. Well, good news. It's the same math. Going to be molarity times our liters. So now we got 0.50 molar times our 0.0280 liters. 0.5 times 0.028, and we get 0.014, 2 sig figs, yep, moles of our base, NaOH. Well, good news, it's a 1-to-1 ratio, right? Theoretically, you could set up an ice table. You could be done, but we know how much of our two species we have now. We have 0.025 moles of this, and we got 0.014 moles of our base. If we're just thinking about what's going to happen here, these are going to react together, right? But one of them is going to run out first. We're going to have a limiting. We're going to have some excess. And so if we're just thinking about what's going to happen here, which one gets used up? Which one's going to run out first? It's a 1-to-1 ratio. And so the one we have less of, our base, is going to get all used up. It gets all used up. Going to be 0 of that left. We're going to have 0.014 getting that used up. So 0.025 minus 0.014. We got 0.011 moles of our hydrochloric acid still unreacted, still floating around in the beaker. And yeah, we'd make some water and we'd make some salt, but we don't really care. That's making salt water. It's just going to float around. Neither of those are going to affect the pH of the solution. But we do know this leftover acid will. So now we know the moles. We want to find the pH. Oh, well, shoot. All right. Well, pH is equal to the negative log of the hydronium concentration. Oh, we need concentration. We got moles. Molarity equals 0.011 moles divided by the new total volume. So it's going to be 0.05 plus 0.028. So we're going to be 0.0780 liters. New total volume. We've technically diluted into more water. 0.011 divided by 0.078 is going to give us a molarity concentration of 0.141 molar. We're going to plug that then into our pH calculation because we know this is now the concentration of our H+. It's a strong acid. It dissociates completely. So negative log, nope, wrong button. Negative log of our answer from our previous problem gives us a pH of how many sig figs? Looks like 2 sig figs, 0.85. Our pH would be 0.85 for our final answer. And this makes sense. We had extra acid in the beaker. Extra strong acid to be precise. Makes sense that the pH would be very, very low. So if you got strong species, find your moles, figure out which one gets used up, figure out how much is left over of the other one, and then solve for your pH just like we normally would. The new caveat here is that we would have to account for the fact that the volume has changed. We had to add those two volumes together to kind of get that new total volume. Cool. You're probably not gonna like this. These are the easy ones. Let's take a look then at our weak species. Our weak species get a little more involved. Sorry, there is an additional one here. If you are so inclined and would like to try one of these for yourself, feel free to pause it and give this a try. It's going to be similar to the last one, just slightly different values. Let's take a look when our species are weak, because it gets a little more complicated here. So we want to figure out what the pH is going to be during each of these points of our titration. And so this is for propanoic acid. It's got a Ka, meaning not all of it splits apart. That also means we're going to end up forming a buffer. Oh boy. Okay. After each of the following, cool. So first and foremost, if it was me, figure out your moles of acid. That's never going to change. The moles of acid are the number of particles floating around in there. Molarity, we know, is going to equal moles over liters. Moles over liters. We know the starting molarity and volume of our acid. So if we want to solve for moles for our acid, for this propanoic acid, we know it was a 0.1000 molar solution. Take that times its volume of 0.0400. Ooh, 4 sig figs? Yeah, 4 sig figs liters. And we now know, I think it's going to just slide us over one. We're going to have 0.004000 moles of our weak acid floating around. That is going to be our starting initial amount for this acid. That's never going to change. In fact, I'm going to clean this up. I'm going to verify that number just because I did that in my head. Yeah, cool. Two zeros and then a 4. All right. Let me clean this up a little bit so we can kind of see what's going on. Cool. So we got our moles of acid. This isn't going to change. We got 0.004000 moles of this. Yay. Cool. And then we're slowly going to be adding, over the course of this kind of titration, we're going to be adding more and more of our sodium hydroxide. And so my next step, I want to figure out how many moles of base are going to be in my beaker. Again, the volumes are going to change here, but the number of base particles, the moles of base, is going to be the same. Doesn't matter if the volume changes. So we got to get into our moles again. And we're changing. We're actually going to have different moles of base at different stages of the titration. At first, we don't have any. So there's 0 moles of NaOH at this point, right? Cool. If I do my molarity times my liters for part B, I should end up with, I'm going to do this math in my head, 0.003, right? Because it's going to become 0.03 liters times 0.1 is going to be 0.00. Now this is moles of, I'm just going to abbreviate OH minus. We don't really care about sodium. This is going to be 0.00400 moles of our base in part C. And we'd have 0.005000 moles of base in part D. So all I did was took our molarity of 0.1 times the liters to get moles for each of our different points of our titration curve. Cool. So now the question becomes, what's going to happen? If we're just thinking about our reaction, we got this equilibrium, and that's kind of what we got down here in this example, but that's not really what's going to happen first, right? The first thing that's going to happen when you add a base to this solution, it's going to neutralize some of this acid. It's going to use up some of that acid. But keep in mind, when it does that, let's look at that major reaction real quick. So we're actually kind of describing two reactions. We're going to have some hydroxides reacting with this weak acid. That's a strong reaction to make some water. And some of our conjugate base. And so essentially what happens is over the course of this titration, this is going to get used up and our our conjugate base is going to be formed. We kind of looked at an example problem like this, but we just hadn't kind of set it up in this format before. So now that we've kind of talked about that, let's talk about what happens then. At this first stage, when there's no base added to the solution, the only thing that happens actually is this equilibrium. Some of it splits apart, and we end up with some hydronium in solution. And for that, we can just use our Ka. Ka is going to equal our propanoic concentration times our H3O plus concentration all over our original HPR. And now technically we wouldn't need moles for this first one because we know what our molarity was. I think we can plug in our values here, can't we? Because we know the Ka. Our Ka was 1.3 times 10 to the negative fifth. That's going to equal, well, we didn't know what these were, right? So it's going to be, I think, x squared, right? If we call this x and this x, that's going to be x squared. So we're technically using our ice table here, all over initial concentration of 0.1000 molar. Cool. So now we can solve for x, right? We take 1.3 times 10 to the negative fifth times 0.1. Square root of answer gives us an x value for this first one of 0.00114. And that's molarity of H3O plus. We can take negative log of that to get the pH. So negative log of our answer gives us a pH, a starting pH. Starting pH at 0. Let me squeeze it. Where can I squeeze that in? So at 0.0, we've got no base added. The only pH we got is coming from our acid split apart. I got 2.943 for our pH for this first one. Don't have to worry about the base. There's no base in there yet. So all we've got that's going to affect our pH is going to be how well that acid splits apart. But now, we kind of got ahead of ourselves here a little bit. We started doing all these mold business. Now we got to take into account the fact that we're adding some base. We add some base to this equilibrium. That's going to neutralize. So I'm looking at part B now. I'm actually going to use up 0.003000 moles of my acid, right? It's going to get neutralized by this base. And every time that happens, it's going to make 0.00300 moles of our conjugate. Originally it was 0, but now there's going to be some in there. So after I've kind of neutralized, at part B, I'm not going to have 0.00100 moles of my acid left over. I now have 0.00300 moles of my conjugate base floating around in there. I have a buffer system. I have a buffer solution. Well, how do we solve for the pH of a buffer? I hear you cry, Henderson-Hasselbalch. We can use our Henderson-Hasselbalch equation, where the pH of the solution will equal the negative log of the Ka, or the pKa, if you will, plus the log, can I get in there? It's going to be tight. Plus the log of the A minus over HA. Probably can't read that. It's really little. You know the Henderson-Hasselbalch equation. We got it. Cool. But we're in moles. Technically, isn't it molarity for that final kind of term on there? Good news, they're in the same beaker. And so if we took these different moles and divided by the new total volume, new volume being, looks like 70 mils, you'd end up with 70 divided by 70, which actually cancels out. We can actually sneak a little bit here and shortcut our work. We want to know what the new pH is going to be. We're going to take the negative log of Ka. Well, Ka was that 1.3 times 10 to the negative fifth. That's going to be plus the log of my A minus, which was 0.00300, divided by my remaining, sorry, I think there's extra zeros on there, my remaining weak acid that's still in solution. Cool, so now we can solve. I'm going to go ahead and take negative log 1.3 times 10 to the negative fifth. That's going to be plus the log of 0.003 divided by 0.001, close parentheses. I got a new pH for my buffer of 5.36. What do we got? 363. And I think 2 sig figs technically, looking at my math here from my Ka. So 5.4. I would take either. We're being pretty loose on our sig figs for this unit, just for sake of time. And this makes sense, right? I'm going to add that above B. I know we're getting a little messy here, but we can make it work. I now know that at B, my pH went up. This makes sense. We added a base. pH should go up. So at B, our pH would be 5.4. Cool. Let's take a look at C. Oh my goodness, C. What's going on at C? Well, at C, we've got equal parts. Oh, we got equal parts. Let me erase because we know how many moles we originally started with here. Part C. Oh boy. Oh boy. I think we're at the equivalence point, aren't we? We've now added as many moles of base as we had original moles of acid. So we're going to neutralize all of our weak acid. All of it gets changed into moles of conjugate base. Okay, so now there's none of that. And now I've got 0.004000 moles of my conjugate. Now, wait a minute. The conjugate of a weak species is a strong species. Oh, boy. Oh, boy. So now we've got floating around all PR minus. But some of that's going to react with the water to form some new weak acid and some new hydroxide. This is why at the equivalence point for a weak acid, your pH is greater than 7. We talked about this on one of our previous videos. So at the equivalence point, we got to use the KB to find the new pH. Okay, because all right, we're making some hydroxide. We need to find the KB, but good news, KW, which is a constant, 1 times 10 to the negative 14th, never changes, equals Ka times KB. We know our Ka from the problem was 1.3 times 10 to the negative 5th. That's going to be equal to our KB. So we can divide over our 1.3 times 10 to the negative 5th. Burp. Solve for just the KB. Looks like 1e to the negative 14th divided by 1.3e to the negative 5th. Our KB is going to be 7.69 times 10 to the negative 10th. And so now we can figure out what our hydroxide is going to be. Yeah, going to be a little bit of an ice table here, I think. We got, but we need molarity. Oh, we need molarity of our propanoate. Okay, well, that's okay. We know it's 0.00, right? Because we know how much propanoate is floating around in there, that conjugate base. It's 0.004000 moles, excuse me. So if we take that divided by our new volume, 40 plus 40 is 80, which is going to be 0.080 liters. We get our molarity of our propanoate. I'm going to put it down below because we're getting a little congested here. 0.004 divided by 0.08 gives us a molarity of our propanoate of 0.050 molar. That's going to technically go down a little bit, but not much. Right now we got none of those. They go up by some. They go up by some. I get to ignore this because 10 to the negative 10th is really little. That means at equilibrium, I'm going to have essentially 0.050 molar of this, some X, and some hydroxide floating around in solution. Okay. Well, now we can use our KB because KB is going to equal our HP times OH minus all over our propanoate ion. So cool. I know 7.69 times 10 to the negative 10th. It's going to equal X squared over our propanoate concentration of 0.050. I can solve for X squared. So we got our 0.05 times 7.69 times 10 to the negative 10th. And square root of that gives me my X. I get an X of 6.2 times 10 to the negative 6. Wait a minute. What was X? That's the molarity of our hydroxide. Negative log of that should give us our POH. We get a POH of 5.2. 14 minus the POH gives us a pH of, survey says, pH of 8 two sig figs, 8.8 on our pH scale. And this makes sense. pH should be above 7 for a weak acid strong base. So now our pH is equal to 8.8 on the pH scale. Oh my goodness, we're so close. Just got one left. Hang in there. Cool. What's floating around now? Oh, nice. This one's easier. I promise. This one's easier because what's floating around now? I think all that's floating around now is going to be extra base, isn't it? We had some acid. We had some acid in here, right? If we're just thinking about what's floating around, we're actually, okay. Our limiting reactant now switches to be the acid. I think we have less acid now floating around because we know we're adding for part D 0.00500 moles of OH minus, right? And we're going to use up 0.00400 moles of our HA, but that's all the HA. It's all gone. And we're going to have 0.00100 moles of hydroxide in excess floating around. Oh, shoot, this is easy. That's a strong base. It will always stay dissociated. So if we find our new molarity, so we take those moles and we divide by our new total volume, which looks like it's going to be 40 plus 50, which is going to be 90 mils. Molarity equals moles over liters. We knew we had 0.00100 moles divided by our 0.0900 liters. This will get us our molarity of the hydroxide. So 0.001 divided by 0.09 gives us a molarity of 0.01 repeating. I'm going to do 3 sig figs. I think we're going to drop it down. Oh, no, I think it's 4 technically, right? Yeah, it's going to be 4. Another one. Cool. That's the molarity of the hydroxide. Negative log of that will give you the POH, which is 1.95. 14 minus our answer. That's a plus. Minus our answer gives us a pH of this excess hydroxide. A pH for our final of 12.0. 4 sig figs, right? 12.05 if we're following our sig fig rules. 12.05. And this makes sense. We have extra base floating around. It should be pretty high on the pH scale. Oh my goodness. That was a lot. Let's work it on back. So really, there's going to be 2 types. All right, let me get back to my PowerPoint there. There's going to be 2 types of calculations that we're going to see. All right, it's either going to be a strong acid and a strong base, or it's going to be a weak acid and a strong base. If they're both strong, find moles of both, figure out how much is left over of your excess, find the molarity, solve for the pH. Figure out what's left over, solve based on what's left over in the beaker. If it is a weak species, things are a little trickier. Find moles of both. At 0 mils of base, you're going to use just the Ka, ice table, Ka and ice table. If you're in that buffer region where you got some of both, Henderson-Hasselbalch. If you're at the equivalence point, you use the Kb and an ice table. And if you're beyond the equivalence point, you're just going to use however much of the excess base you got and solve using your molarity equation. So the trick here is going to be to figure out what's actually floating around still in my beaker and then solving accordingly based upon what you've got. Feel free to rewatch. We're going to be looking at a bunch of examples, problems of this. I just wanted to get you a real solid example problem to start to see this in action. Make sure you've got the notes and come with questions for when I see you again later in class. Have a great one.